Hi, everybody. Anyone mind if we get started? Okay, great. So I hear that the people listening on the internet can't actually see the room, which is great for me because I can tell them that there's hundreds of people here. There's no empty seats. Everyone's super interested. Okay. So I'm excited to be here with everybody. How many of you are postdocs? How many are postbacks? Okay, how many are other? Great. Are you guys summer students? What's a visiting grad student? Okay, great. Well, thanks for joining. So that breakdown fits pretty well with the way I've organized this talk. I'm trying to keep it at a pretty high level because I know this course is just massive. There's so much about fMRI that they're trying to fit into this course. And so I'm trying to be sensitive to that and keep it at the level of sort of what can we do, what are people trying to do, and what's the big picture for this topic. And this topic is, of course, predicting performance with fMRI. And so along those lines, I'm going to talk about the following things. Why are we predicting performance? How can we predict performance? We're going to break that down into sort of performance as a trait, something that's stable over time, your inherent ability, and something that's a state, like mind wandering or sustained attention or task engagement that waxes and wanes in the same individual. And then we'll talk about intervening to improve performance. And all of this is pretty high level, so I'm going to take a little time at the end and talk about one particular study that I've been working on where we're trying to predict someone's performance on a reading recall test from their fMRI scores as they read. And that'll give us a chance to look at the details in one particular case. We'll talk about confounds, always important to keep in mind, and what we can conclude from all this. And along the way, I'm going to be linking a little bit to past lectures, especially the individual differences lecture that Emily Finn gave and machine learning lecture that I think Martin Habar gave, but maybe Francisco? Okay, yeah. How many went to the individual differences lecture? Okay, just a couple, so I don't have to worry too much about overlapping there. All right, so why are we predicting performance? First, it's important to define what this is because it's a little vague. The dictionary definition is the action or process of carrying out or accomplishing an action, task, or function, which I summarize as doing a thing. This is about as vague as you can get. So for our purposes, we're going to define it as an individual score on a test of cognitive abilities, symptom severity. This is in the moment, not sort of a retrospective survey, or educational achievement or something like that. And this is important. It's often pretty central to a patient's mental health complaint. They'll come in saying, I can't remember things like I used to. I can't think quickly enough. I can't remember words. And those sorts of things are a form of performance in our everyday lives. So that's the performance part. What about the prediction part? I think prediction is hugely important, and it's something that a lot of studies go through their whole cycle without thinking at all about. So I want to give a quick introduction. For a long time, neuroimaging was just focused on finding group differences. For example, the amygdala of a depressed person responds more strongly to negative stimuli than the amygdala of a healthy person. But over time, people started moving towards looking at individual differences or performance differences. Maybe an individual's level of amygdala reactivity could be used to predict their score on a test of negative affect. So now we're looking at not just groups, but individuals and more graded levels of behavior. But the really exciting part comes when we start to predict individual outcomes. That is, how well will a certain individual respond to a certain kind of treatment, or how at risk are they for suffering from a certain condition in the future. And this is exciting because it gives us the chance to use neuroimaging to sort of save someone the trouble of going through a long and costly treatment, or maybe to help them get the most likely successful treatment right away, rather than having to go through options A, B, and C that aren't well suited for them. I'm not the first one to observe that there have been thousands of neuroimaging studies, and hardly ever is fMRI used in the clinic. And this idea of prediction is a possible way that our imaging studies can find their way into the clinic and help people in the short term, not just in the long term of understanding the brain better. And along the way, looking at performance differences and individual differences can shed new light on neural processes. So in a block design analysis, you might say, this region up in the upper left responds more strongly to task than rest, while the others don't. So we might say this is the region that's important for performing this task. But we might start to look at an individual differences framework or a performance prediction framework and find that there's actually another region where people who perform better on this task have stronger activity in this lower right region than people who don't. Even though on average across the group, it doesn't look like anything's going on, by looking at individual differences, we can say, hey, maybe this region is also important for performing the task and performing it well. And by doing this kind of thing, we can help make brain-based diagnoses and classifications, not based on what symptoms you have or complaints you have, but based on what's different about your brain than the typical healthy volunteer. And this is part of the promise of moving from a DSM kind of framework based on symptoms to an RDoC kind of framework. How many have heard of RDoC before? Okay. The whole promise of RDoC is, finding levels at which different people are have different levels of brain activity during different tasks, or have different sort of biological responses that might help explain the symptoms that they're seeing. People who are in charge of the RDoC would be quick to say this is not something they're trying to replace the DSM with, it's more of a supplement. Can we not only describe their symptoms, but also what's different about their brains? And once we do that, once we get a sort of brain-based diagnosis, we can suggest targeted interventions. If you find out in your scan that the reward network is changed by performing this task, then that suggests a cohort of drugs or therapy that might target that reward system. Or if it's not a system that, even if it's not a system that's well known to be linked to drugs, then you can still try to do targeted therapy in the form of deep brain stimulation, or even shallow brain stimulation, or something like neurofeedback, where the person uses their own brain activity read out to them to try to change it. So to summarize, we can use prediction performance to shed light on neural processes and individual differences. We're making brain-based diagnoses and classifications down the road, and hopefully to suggest targeted interventions that might be useful for this specific person. So that all sounds great. How do we do it? Well, the short answer in a lot of cases is machine learning. Machine learning, as we all know, is a magic box where we throw the brain into a funnel, it goes into the box, and out comes the magic that you were hoping for. This is how it's often described. And as usual, if there's a science joke, XKCD has already made it better than I could. But the important point I want to make is that you still have a role. Even if you want to use machine learning, you need to select your features. This is a combined effort between you and the data. So how many have heard of a machine learning feature before? Okay, has anyone not heard of a machine learning feature? Okay, I'll go very quick then. Here's your general definition, and we're going to look at the specific case of telling the difference between turtles and cats. We're teaching a computer to tell the difference. We could, as it's learning to tell the difference, we could give it information about each animal, like its length and weight, but if we do that, turtles and cats are about the same length and weight, and so these features are not going to be very helpful to it. If it tries to draw a line between these dots, where every green dot is a turtle and every orange dot is a cat, it's going to have a hard time doing it because they're not well separated. But if we chose a different set of features, like age and speed, well, turtles tend to be a lot older and a lot slower than cats, and so in this space, where age is one dimension and speed is another, we find that turtles are on one side of a line and cats are on the other. We can teach our machine learning classifier to draw a line between them and tell them apart. So the point is, you have to tell the machine which features to look at. And in some cases, fMRI magnitude, the things we use in most of our studies, is a good choice. If we want to look at good performance or bad performance, we might find that in some ROIs, activity is high during good performance and low during bad performance, or vice versa. And so we might say that the activity in ROIs 1 and 2 are indicative of good or bad performance. But we might look at some different ROIs and find that the signal is about 0 in both cases. So fMRI magnitude doesn't tell us that much. But if we look at the correspondence between these two ROIs, we might find that in good performance they line up, and in bad performance they don't. And this is described as having high functional connectivity or low functional connectivity. So in this case, fMRI magnitude is not a very good choice of features, but functional connectivity is. So we might use what we call a functional connectivity edge between these two regions as one of our features to predict good versus bad performance. And of course, if we looked back at the signals in ROIs 1 and 2, they have low functional connectivity in both cases, so functional connectivity is not a great choice. So we have two ROIs where magnitude is better than connectivity, two ROIs where functional connectivity is better than magnitude. And you have to think carefully about which you want to use as your feature space. If you decide that you want to use functional connectivity, you can use whole brain functional connectivity, where you parcellate the brain into regions, and you look at the connectivity between every pair of regions, and then use machine learning to select a set of edges, set of pairs of regions that you think are important for this classification of good or bad performance. And the hope is that the mean functional connectivity in this set of edges, perhaps with a weighting determined by a machine learning classifier, indicates that an individual is going to have higher or lower performance on your behavioral test. Does this make sense to everyone? Okay. Any questions before we keep going? Okay. You can also use something more complex like MVPA, multivoxel pattern analysis. And in this case, we might find a region in inferior temporal cortex where there's a certain region that predicts whether you're seeing a face or not, based on not the overall activity, but the pattern of activity, voxel to voxel. And we can use the similarity to that pattern to predict whether or not they were seeing a face. And you can use similar methods that we'll talk about later to predict whether they were performing well or not on that face-related task or object-related task. So the point is, this is all combining your knowledge from the literature of what makes a good feature, what you should tell the machine about, with the data's ability to weight across those features and say which ones are important and which ones are not for this specific thing I'm looking at, good versus bad performance. So let's talk about what people have done so far. Performance as a trait. This is the idea that your performance is a stable property of you, that it's going to be the same over time, or if you tested them multiple times. So one area where this has been studied in the past is working memory. People found that on an NBAC task, people who performed better on the task had stronger negative functional connectivity between the default mode network and a working memory network that they defined from activation in the task. So these are groups of regions that tend to move together, and they sort of considered them as a whole and looked at the connectivity between them. Does their activity correlate more or less? And they found that they tend to be anti-correlated, and that anti-correlation is stronger if you're performing well on this task. That was one where they set a strong hypothesis going in, and so they just looked at that one value and said, is it high or low, and can we use that to predict? You can, of course, also do a more data-driven approach where you say, I think it's one of these connections between these sets of regions, but I'm going to let the data tell me which one by giving it lots of examples and letting it tell me how I should find a weighted average. And this is one case where that was done. This is a study at Yale where they gave people a very simple image recognition task. Is this a scene? Is this an outdoor or an indoor scene? And they found a whole collection of edges of the functional connectivity matrix, which in this case are plotted with a red line between two regions that had stronger connectivity in good performers, and a blue line between pairs of regions that had strong connectivity in bad performers. And they found that if they took the average connectivity in this network, that good performers had higher connectivity than bad performers. They could do a decent job of predicting which was which. And that was with a very simple machine learning method that I almost hesitate to call machine learning, called, what's it called? I'll get to it later. But this method is used in a number of different studies. Even though it's very simple, it's been used successfully to predict sustained attention, reading ability, which we'll talk about later, ADHD and autism symptom severity, creativity, and even personality traits like neuroticism and narcissism. So you can see that none of these predictions are strong enough, none of these correlations are strong enough to sort of replace the test that they're using to predict. But they're showing us that there's something in the brain's response to, something in the brain's organization, in its functional organization, for which regions are correlated with which other regions, that can tell us about that person's behavior in the real world. And this has led to the idea that there's a sort of suite of networks that might predict a suite of abilities, and that with just one resting state scan, you can look at the connectivity in each of these separate networks and predict how well they would do on a number of different tests and scores and measures. So this is a form of performance prediction of their performance as a trait. We can also think of performance as a state, and this is often called mind wandering or sustained attention or task engagement. And these are often tested with a really simple task where it's easy to do just one trial correctly, but if you're asked to do it for 20 minutes straight, your attention is going to wax and wane, and you're going to miss some things. The SART is one sustained attention to response task. Another is called the GRAD-CPT. This is the gradual continuous performance task where images fade into one another. And they're essentially go, no-go tasks, where most of the time you respond, but every once in a while the stimulus tells you you shouldn't. So if you get into the zone of respond, 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 you might forget to not respond when you see a certain stimulus. And pretty early on, people found that there's different activation in the brain when you miss something, when you perform poorly, than when you're performing well. And they found this whole set of regions that have higher activation just before you make an error in the SART task than it does when you're performing well. And that's on average, but it led people to the idea maybe we can predict these in advance and maybe even intervene to help them perform better. And so this is one study that tried to do that using not only pre-stimulus activation, but also pre-stimulus functional connectivity. Whoops. Pupil diameter just before the stimulus was presented, and the pupillary response to the stimulus, all combined into one great big multimodal classifier, and giving about a 70% accurate test of whether or not they were going to perform well or poorly on this on a given trial of the SART task. So the difference between trait and state is this idea that it's time-limited performance that can vary from moment to moment. Working memory is a popular one for trying to predict performance. People found in 2002 that even here at the NIMH, that there were signatures in a number of regions that predicted whether they were going to perform well on a given working memory trial. And on a meta-analysis of sort of subsequent memory or forgetting, if we show you a bunch of stuff now, can we look at your brain activity and tell whether you encoded it well enough to remember it later? They found that there are a number of regions that also predict your proper encoding of a stimulus, and that it changed slightly based on whether that stimulus was a word or a picture or an association between words or an association between pictures. So this sort of study, it can help us learn more about how memory is operating, what happens when memory is failing, and what we might be able to do to help people who are having trouble with their memory. And one of the things we might be able to do to help is intervene in one of these ways we talked about before, with drugs, with therapy, brain stimulation, or neurofeedback. And it turns out at least 2 of these have been tried before, and we're going to talk about them now. That attention network that we mentioned before, this is the grad CPT task where images of indoor or outdoor scenes are displayed, and it's very easy unless you stop paying attention. We found this high attention and low attention network down here, a whole set of regions. So they said maybe that's correlation, maybe it's causality. Let's see if we can, what happens when we give people Ritalin. Will we see a difference in this functional connectivity strength? And they found that yes, there were a number of functional connectivity edges that were affected by Ritalin, and that these high attention and low attention edges were among those edges, among the ones most affected by this drug. So that could tell us that, give us some idea of what Ritalin is doing, why it might be helping, and how we might be able to make future drugs that could be more effective by targeting the specific edges that are important to this task. A really cool effort at neurofeedback was performed at Princeton, where they used MVPA patterns. Remember, these are the voxel-to-voxel patterns that predict what kind of object you're seeing. To sort of, they found out, how we can use that pattern to tell if someone's looking at a face or a car, or a face or a scene, I guess it was. And then they said, we think that in good performers, our classifier will be really able to separate those two well. Whereas if you're starting to zone out, then the pattern starts to look like each other. It looks like noise. It looks the same whether or not you're looking at a face or a scene. And to put that to the test, they made this neurofeedback setup where they perform this multivoxel pattern recognition in real time. They decide how well it's performing. If it's performing badly, they think that you're performing badly, and so they feed that back to you by making it easy or hard, and that helps people wake up and perform better on the task. So they found that with this neurofeedback, people could improve their performance on this task. And that's a way of sort of cutting out the middleman of having to find a drug that targets a specific edge of the matrix or a specific region of the brain. Maybe we can allow the person to look at their own brain activity and just sort of try things until they're able to make their brain activity more like that, the brain activity that they want. Do we have any questions before I keep going on? I know I've been going very quick. But I think this is an exciting application of neuroimaging. I think this is starting to get us close to the promises of personalized medicine, or even of better understanding what's going on in a person's brain when they're having problems or when they're doing great. These are the sorts of things that get me really excited about neuroscience. So next I want to talk about one study that I've done, and that is extending some of these methods to predict reading recall ability. This is something that's hugely important for your academic success, for success in a job. Can you read something and retain it? And so to test that, the other thing I like about it is that you can do it in the scanner pretty much the same way that you do it in real life. And to that end, we had this, what we call a naturalistic reading task, where we show a page of text on the screen. People are asked to read it at their own pace, and as they do that, we play sounds, distracting sounds, either white noise or irrelevant speech, just to sort of simulate reading in a noisy environment. And after they do that, we ask them questions about what they read. And we find that there's a pretty good distribution across people of how well they perform. Some people remembered a lot, some people not so much. And what we tried to do was use functional connectivity to predict how well people would do on this reading recall test. So remember, this is breaking up the brain into parcels. And then if we consider each region to be one of these lines, we might notice that in this person, there were high functional connectivity between these two regions and low functional connectivity between these two regions. And let's say that that person was a good reader, and in a bad reader, we see the opposite pattern, where the top two had low functional connectivity and the bottom two had high functional connectivity. So both of these are informative. Both of these might be usable to tell us whether someone's a good or bad reader. They're just useful in opposite directions. So we might call the top one a positive edge, the bottom one a negative edge. And the hope is that we can use the average sort of weighted connectivity in these edges to give us a good metric of reading recall. And in fact, that's what we found. I'm going to be glossing over some of the details here. But using this method, we found that there are a number of edges with stronger or weaker connectivity and good reading recall performers. And that by using these edges, we can get a pretty strong correlation between brain and behavior. It's important to point out that this is leave one out cross-validation, and that gives us a bit of a boost, but we can use, cross-validation, we can use permutation tests to get a decent idea of just how unusually good this performance is. So in trying to figure out which regions are important, we started by comparing this to things that we might have expected from the literature. So the default mode network might be a good metric of how engaged someone was with the task. You might expect that it has higher connectivity and bad performers because they were zoning out or their minds were wandering. But in fact, there's very little overlap between the default mode network, which we defined from Neurosynth, and our reading network. Similarly, you might think that language networks were important. Either looking at Neurosynth terms like reading or speech, topics like that. We might expect that these might have higher or lower connectivity depending on whether you were attending to the visual reading or the auditory speech. But again, we find that these regions were not the ones that our more data-driven approach picked out. In fact, if we just look at the regions that took part in any way in this reading reading recall network that we've defined, we find that this is different even than a sort of GLM of reading versus fixation. So it's not just that these regions are having higher activity and therefore higher connectivity with each other during the task in good performers. It's just that there's something changing about the functional organization of these regions, about how well they're correlating with each other. So this is one way that we could predict how well people are going to perform on this reading recall test. We could also use these other networks that we pointed out, or we could use more behavioral tests like the rate at which they saccade. There's some studies out there that show that good readers saccade more and their pupils dilate more than bad readers do. And so we wanted to put that to the test. And so we tried to use each of these to predict how well the subject was going to do. We also used the sustained attention network that we talked about before. That's the one that showed up in the Ritalin study. And we find that, if I can go back just a second, we find that the reading network we've defined outperforms all of these others. But some of these more general metrics, like the default mode network and the sustained attention network, and even pupil dilation, do a decent job of predicting how well someone's going to perform in the scanner. And so this might lead us to ask, can we combine these in interesting ways? Can we use what we've learned from the literature and what we learned in this data-driven approach together to get an even stronger prediction? So the dumbest way I could think of doing that was just combining all these edges together into this huge super network and looking at the average connectivity in all of these edges. And we find that if we do that, we get even a small boost above what the data-driven reading network was giving us. And we're getting pretty close to ceiling, so even a small improvement can show up as statistically significant. And we can test that by using partial correlation to see if we're getting a good chunk of the variance that's left, or by using something called a Steiger's z-test that helps us compare two correlation values. So in this case study, we identified this reading recall specific brain network. We found that it used different brain areas from attention and language metrics. So again, this is a way that we can sort of shed more light on the neural processes that lead to reading recall. It has predictive information beyond other metrics, so there's an advantage of using machine learning methods and a data-driven approach. And this information is not redundant with other metrics. You may be able to use them together to boost prediction. And one area I'd like to take this into is sort of within subject prediction, looking at, rather than a trait approach, a state approach. Can we predict when someone's going to have a good or bad moment of remembering what they're reading? And if we can do that, can we sort of intervene to try to improve people's retention? Could we take a look at their brain activity after they finish reading and say, looked like you zoned out during this part and this part of the reading. Why don't you take another look at these pages? And when doing that, I want to use context. To the eyes rest longer on more unusual words. We have information about what they're reading, not just that they're reading, and we can use that to make better classifiers, to give a better feature selection up front. Any questions before we move on? Okay. I want to talk about confounds. Oh, yes, please.
Well, I have a quick question.
Sure.
You defined the reading network, right? I was just wondering, why are those nodes selected as it? Although, what are the principles behind neural principles behind those? I saw all temporal regions are as well as nodes.
Right.
I was just wondering, why those be according to the reading code?
It's a good question. I spent a lot of time puzzling over this and looking at the individual regions. In some cases, it makes a lot of sense based on what we've seen in the literature. So this is a visual task where people are making sense of what they see semantically. And so one of the main source of positive edges that had stronger connectivity and good performers was edges between occipital regions, visual regions, and left temporal regions, semantic regions. So you can think of that as having a stronger pipeline of communication between visual and semantic areas. That makes a kind of sense. There are others where you wouldn't have picked them out so readily, but they do have some evidence for being involved in reading. There's a lot of evidence that cerebellar regions and right frontal regions had stronger connectivity in poor performers. And that I would never have guessed. But turns out there's a rich literature of cerebellar activation in reading. People aren't sure quite what it's doing. And frontal regions, I think, are probably maybe showing up in this task because we have a long narrative. In a lot of reading tasks, you have just single words, but Ori Hassan and his intersubject correlation analyses have shown that when you have a longer narrative in a story, whether it's written or spoken, then some of these frontal regions are showing that they sort of come online, that they're showing consistent activation. So that's my guess, but it's hard to tell. And one thing that I like about this is it's uncovering new regions that we might be able to make testable hypotheses for. Yeah. Yes.
I have a follow-up question on this.
Sure.
So what is the criteria for a region, for a node to be involved in a reading network? Is it like a certain radius? And for the language network, because it doesn't overlap with the reading network at all, which seems very surprising to me. I was wondering, did you do a language network, or is it just anatomical evidence?
Right. Okay. I'm going to try to repeat the question, which I forgot to do. I'm sorry for the first one. The question was, how are these reading edges selected, and how are the language regions selected? And isn't it surprising that there's no overlap? So I did gloss over this, and then in the interest of giving a 10,000-foot view, but I'll try to get into a little bit. Essentially, we evaluated each edge individually, and we said, does this edge, these pair of regions, have a connectivity that varies consistently from good to bad performers, either in the positive or negative direction? So most machine learning methods would sort of look at a weighted average across all the available edges. This one just looked at each individually and said, is this a strong enough relationship to say it's important? And if it is, then we include it in our network. So this doesn't give us a set of weights so much as just a binary for each edge. Is it positive, negative, or not strong? Not strong enough to be included. So that's how we selected our reading network edges. The language network was based on a meta-analysis from Neuroscience. So we just found a topic that we thought was most closely related to visual language and one that we thought was most closely related to auditory language. And we selected any connections that were between those regions that showed up in those meta-analyses. So I can't tell you that that's the exact right way to do this, but I tried to think, if I were trying to do this just from the literature, how would I have done it? And that's the way that I came up with. Now, why is there no overlap between that way of doing things and this data-driven way? It may be that the old tasks were different enough from this new task that the activation is different. That's very possible because we're adding a lot of new levels of complexity. Another possibility is what I laid out in the beginning, the idea that the areas that are activated by a task might be different from the ones that are differentially activated or connected across individuals. So there's some evidence for that when we compare the regions used in our network to a regular GLM of reading versus fixation. Different regions show up there. And so what we might be seeing is there's a difference between group studies and individual different studies. Did I cover all of your question? Okay, great. I don't want to give the impression that this is the be-all and end-all of reading networks, and now I have the right one, and everyone else can stop doing reading studies. Far from it. But this was my attempt to take a pretty well-studied topic of reading and look at it in a different way that takes advantage of these latest studies in functional connectivity and individual differences. So let's talk about confounds and conclusions. The reliability of your MRI signal depends on the reliability of your performance measure. This maybe goes without saying, but I'm going to say it anyway. Things like IQ and how well they're going to comply with the task might change if they're a kid who's easily frustrated and has outbursts. These often co-vary with conditions. One way to get around this, one way to deal with this, is to collect multiple performance measures. And then you can say, how sensitive is this to the performance we're trying to measure? How specific is it? Or how much is it just general good performance or bad performance on anything? that can give you an idea of how much to interpret this as the reading network and not just the good performance network. You also have to decide whether you care. If the purpose of your study is just to predict, then you can use everything you can get your hands on. You can use how much they move in the scanner, you can use their IQ, you can use all these covariates just to boost your prediction. But if you want to learn something about the brain, a lot of times you have to be very careful about these things. MRI confounds are always a source of anxiety. You know, these can lead to fMRI signal changes that are not coming from brain activity, they're coming from artifacts. You've probably heard about motion artifacts in a previous lecture in this course. You won't be surprised to learn that it often covaries with conditions. Someone with ADHD is going to move more in the scanner than someone without it. You can mitigate this by using pre-processing and censoring very carefully. And again, you can refer back to previous lectures on the best ways to do that. You can use motion-matched participants, try to get individuals within these groups that are similar in how they moved. And you can very carefully look at your data and examine the data results and say, is there any way that I could have missed that this is explainable by motion? When in doubt, ask Bob. To wrap everything up and give a quick rundown of everything we talked about today, performance, as we've defined it here, is pretty central to quality of life, to how well you're able to do in school or perform at a job. Prediction of that performance can be based on many features, and which ones you choose and use are dependent on a combination of your knowledge of the literature and this data-driven selection that machine learning can help with. The performance you're measuring can be state-based, this idea of innate ability, or trait-based, this idea of mind-wandering. And it's helpful to have an idea of which that is before you start your study. When we do performance prediction, we can shed light on neural processes and individual differences. We can start to suggest targeted interventions. And a lot of times these are very testable predictions. But beware, confounds can affect your results and your interpretation. So please be proactive and think about these things before you get too excited about something new you've discovered. With that, I want to give many thanks to those in the section on functional imaging methods who are my co-authors on the reading study, to Raj Ghani from the LBC, who was a summer student with me and helped out on that study as well. Many thanks to my new lab, just joined the Emotion and Development branch in the NIMH, and so thank you guys for coming, and thanks to them for letting me come back and give this talk. And with that, I want to thank all of you for coming and see if you have any more questions. Thanks very much. Any more questions? I know it's a lot, and if you have something specific that you're thinking about doing this kind of performance prediction with, or if you have a specific question about machine learning, all the stuff that I glossed right over with my talk of turtles and cats, feel free to speak now or come and talk to me afterwards. You can also find me on Net if you want to set up an email thread or talk to me in person later. Any other questions? All right, thanks very much. See you on Wednesday.